Hello viewers, welcome to another video. This is PVS the tutor. Under physics, we're going to look at Hooke's law, one of the most interesting laws that focuses on the stretching and the compression of objects, especially springs. Now, when it comes to Hooke's law, all right, we are still talking about the effect of a force. Are we together? So what does this Hooke's law tell us? All right, so Hooke's law states that the extension of a loaded spring is directly proportional to the force applied, provided the elastic limit is not exceeded. All together, right? So the extension of a loaded spring is directly proportional to the force, provided the elastic limit is not exceeded. Now, before I even go anywhere, all right, there are some key terms here that we need to familiarize ourselves with. And most people, they make a mistake and they use them interchangeably. While they are not the same. What are these terms I'm talking about? I'm talking about this term here, the elastic limiting. The elastic limit. Let's define the elastic limiting. So the elastic limiting is the maximum stress. When you say stress, we mean force per unit area or pressure. All right, a material can experience without undergoing what? Permanent deformation. So we are saying a maximum stress or pressure, okay, a material can experience without undergoing permanent deformation. To deform something is to break it or something like that, to change its shape. All right, so the maximum stress or pressure a material can experience, all together. Then we have the limit. We have another term, the limit of proportionality. The limit of proportionality. From now on, you need to know the difference between these two. Now, what is the limit of proportionality? The limit of proportionality, it is a point, all right? It is a point where the relationship, that direct relationship of this extension and the force applied no longer exists. Are we together, right? So we are calling it as the point where the linear relationship of the force applied and the extension breaks down. You've now seen the difference, right? That is the difference between these two. Okay? Now, someone might say, sir, how can I draw that one? Let me show you. So, we will always have the force okay, in one of these, then we can have the extension here. Okay, so the force and the extension, they have a linear relationship, but sometimes this linear relationship can bend like that. Together, right? Assume we have something like this, and let's say at this particular point here, that's where we have they no longer proportional to each other. I think from here it's curving like that, right? So this point here is what we're calling the limit of proportionality. Okay, the limit of what? Proportionality. Then the elastic limit is after the limit of proportionality. It is beyond the limit of proportionality. It means it is the maximum force or stress. All right, the object needs to experience before it is completely. You can say that from here it's bending, but here it's worse. It's completely deformed along this line. So we can say from there, coming down here, that's where we have our elastic limit. But here, this is where the straight line has ended. So we have the limit of proportionality. Are we together, right? Something like that. So now, let's go. The relationship, all right? We are saying the force is directly proportional to the extension x. Now, sorry, to the extension x, like that. Now, in situations where we want to rewrite this relationship into a more equation way, we say the force is equal to, this changes, we introduce the k, which is the constant. That's the constant, we call it the spring constant, then we multiply it by x. So this is the Hooke's law. Together, right? Now, we're not just going, this is at our level, but when we go further, this changes. All right. Where 4F is the force. So we are going to look at examples on how we can calculate either of these. So let me just give you a scenario. All right, let's say you have a spring, right? So this is the original length without attaching anything to it, right? So that is the original length. Let's call it L1 together, right? Let's call it L0 like that. All right. Then when you attach something to this string or spring, so rather, there's an object of a certain mass or weight, you discover that it stretches. It stretches. Maybe this is the box that we attached. Now this box has got a force F acting downwards. In this case, we're calling it the weight, force of gravity. So it stretches into a new length. Let's call that one L1. So what is extension? Extension now is the difference between the final length and the initial length. All right. If this, for example, if L0 was 5 centimeters, and after applying the load to the spring, we have 15 centimeters. Then our extension x will be equal to 15 centimeters, then minus 5 centimeters, giving us 10 centimeters. I think from the word extension means by how much something has been extended. So it means this spring has been extended by 10 centimeters for it to reach 15 centimeters. Is it making sense? So let me put up an example. An example 1. A spring has a spring constant of 150 newtons per meter. What force is required to stretch it by 20 centimeters? Take note, the K in our case, all right, let's look at the solutions. So the K in our case is 150 newton per meter. Then, when they use the word by, it means that's the same extension. But when they say to, don't even dare take that as a constant. All right, extension. So we need to convert this one to meters. By dividing by 100, we get 0.2 meters because we have meters there. All together, right? So what are we looking for? we're looking for the force F. So we know that F is equal to Kx. So this gives us X is 150, then we have 0.2. So what do we get? The F is, I'm getting 30 newtons. Let's go to example number 2. Example 2. A force of 20 newtons is used to pull a spring, causing it to extend by 0.05 meters. What is the spring constant? Again, let's gather the data that we have there, right? So we have our force, 20 newtons. We have our extension, 0.05 meters. We're looking for K, which we don't know. So using our relationship, we can make K the subject of the formula by dividing throughout by X. So we get F over X. Our F is 20 over 0.05 meters. So get our K as 400 Newton per meter. Let's look at another example. Another example is, so in the first stage here, call it A, we have an unstretched spring. This one is not stretched because there's no load applied. So the original length here is 15. Then after applying a load of 8 newtons, you can see that it stretches to all the way to 19 centimeters. How do we find K, which is the spring constant? All right, gather here. To find K, we know that from our relationship is that F is equal to a Kx. So we need to find X first of all. X we said is L1 minus L0. So the one that we have here is our L1. The one that we have here is our L0. So this will give us 19 centimeters minus 15 centimeters, which will give us 4 centimeters. Now that we found that the extension, the force is here, can we fail to find K? No, we cannot. So K becomes force dividing by what? X. The force is 8. Here we have 4. We are getting what? We are getting 2 newtons per centimeter. If they have said convert sometimes they are going to restrict you on the units to convert your length to, but if nothing has been given, just leave it in any units you're comfortable with. All right. The last example, a mass of 2 kg is hung from a vertical spring with a spring constant of 18 Newton per meter. What is the extension of the spring? So what we have here is something like this. Okay. It's something I always advise students to draw what we call a freeboard diagram, which is going to help you analyze the situation at hand. So we have something like this. All right. Then we have a mass, which is 2 kg. All right. Then they are saying, what is the extension? All right. It's like at the beginning you had some, the same one. It was like this, but nothing was hung. So you had the original there. Now what you have here is the final L1. Now that you have, let's collect the data. We have K is 80 newtons per what? Per meter. The mass is 2 kg. The force of gravity has been given to be 10 Newton per watt per kg. So step 1, from our relationship of force is equal to Kx, we need force. And in this case, because the force we are targeting here is the weight of the object. So the force is just the weight of object, which is given by mass multiplied by the gravitational field strength. The mass is 2 kg. The G is 10 Newton per kg. Kg and kg gone. So end up having 20 newtons. So this is the same weight there. All right, now we can now use Hooke's law to find our extension. From Hooke's law, extension is equal to force divided by the value of K. The force is 20 newtons and the value of K is just 80 newtons per meter. So Newton gone. So I'll end up having 0.25 meters. Or you can convert this one to centimeters by multiplying by 100, which will give you 225 centimeters. You've seen how easy it is, right? Now, other examples and so forth, it's just the application, for example, the graphical part and so forth. It's all coming from this concept, okay? So this is what your friends are learning. Even more than this, I'm just giving a demo, and I hope that even with this demo, something has stuck in your mind and you'll be able to help yourself remember something. This has been Previous the Tutor, and this is Genius Pro Online School. Thank you so much. I'll see you next.